But we might see some things that you haven't seen. So density is mass over volume. We call it rho, and it's equal to mass divided by volume. This is the Greek letter rho. It's just the variable that we use for density. Here, mass, or m, is the mass of the object. And of course, v is its volume. And the SI unit of density is then kilograms per the units for volume, which is cubic meters. Just some reminders about volumes. I usually give you these on the exam. In fact, I think they're on the equation sheet. But some volumes that are just useful for you to know. The volume of a cylinder is equal to the area of a circle, that's pi r squared, times the height of the cylinder. It's like you take the area of that circle and then you extend it along the entire height of that cylinder. And then the volume of a sphere, what is it, 4/3 pi r cubed? Yeah, it's 4/3 pi r cubed. There's no quick way to think about how that comes from the area. It's actually an integration of a sphere to find the volume. All right, so those are on your equation sheet. Aren't they on your equation sheet? I'm pretty sure they are. Up at the top left-hand corner. Marissa, are they up there? Okay, well, if you need them, I'll give them to you. But just know that they exist, okay, for the test. But I'll give you those equations. Don't bother memorizing them. I give you some densities here. The density of water, by the way, is 1,000 kilograms per cubic meter. It's really just a value that you need to know, I think, just to be, a well-rounded person, to know the density of water. But do you know what it is in the CGS system, in grams per cubic centimeter? It's equal to 1, right. We talked about this in the lab, but do you know why? Because that seems really strange that the density of water would be 1. Why is the density of water 1? Anybody know? You know? We define it. Like, we have the standard for the mass. What is the standard for the mass? Is that silicone sphere, or we said it was actually a platinum cylinder, but they're changing it. But it used to be that the standard for the kilogram was based on a certain amount of water. They take a certain volume of water and then base a kilogram on that. They don't do that anymore, but that's what the standard used to be. That's why it's such a round number. All right, there's some other densities. Notice that the density of ice and water are different, that ice is less dense than water, and that just seems strange to you, right? That something becomes a solid and then it actually becomes less dense. Doesn't that seem strange? It is very strange, actually, that the solid form of water has a lower density than the liquid form of water. But it's also quite remarkable for us, anyway, that, we're not all dead or living on this frozen planet. Because if it was a higher density, ice, what would happen to our world? The water on the top would freeze, it would sink. The water on the top would freeze, and it would sink. And the planet would be covered in ice. But it's not, because the density of water is actually less. The density of ice is less than water, allowing it. Not many substances that do that, but water is one. So if it were not true, the ice would sink, and we'd all be dead. We wouldn't be here. And the planet would freeze. It would be a very different world if the density of ice was more than that of water. A very, very different world. All right, we're not going to see specific gravity in this class. You won't see it on the test, but I just mention it here because it's used quite a bit in other areas, and you might see it on the MCAT, you pre-med folks. But just to point out that the specific density is the ratio of two densities. So, like, for example, was the ratio, excuse me, I'm sorry. The specific gravity is equal to the ratio of some substance divided by the ratio of water. So, like, for example, aluminum, which has a density of 2,700 kilograms per cubic meter, it's going to be 2.7. 2,700 divided by 1,000 is 2.7. But again, not going to test you on the specific gravity at all. You will not see that, so don't. You got to put a big no next to it. All right. A block of unknown density is floating in fluid. Which of these statements about that block is true? Let me pull up the clicker base here. All right, let's stop at, say, 43. 43. Good job. You are awesome. The block is less dense. That's why it floats, right? That's why ice floats in water. Let's see. Helium atom walks into a bar, and the bartender says, "Hey, we don't serve noble gases around here." Helium doesn't react. Oh, that's a good one. Like you should tell your chemistry. Tell Dr. P that one. He will smile. Does he smile a lot in class? No. But he's a funny guy is the thing. He's a very funny guy.
He lost Paris. No, wait, let's get
Okay, let's look at pressure. Pressure, I'm going to put it with a P, just because that's how I draw my P's. It helps us to differentiate pressure from density, so that's why I draw my P with a little base on it. Pressure is force per unit area. We'll see pressure in a couple different ways. Write this just as F over A. This is on your equation sheet. The density equation is on there too, by the way, but I think that y'all know both of these. The SI unit for the pressure is the Pascal. And it's after the mathematician, philosopher, theologian, Blaise Pascal. 1 Pascal is equivalent to 1 Newton per square meter, because it is a force per unit area after all. We'll also use another unit for pressure. This is often used when we're talking about pressures of gases, is the atmosphere. 1 atmosphere is equal to 1 times 10 to the 5th newtons per square meter, or pascals. 1 times 10 to the 5th pascals. This is abbreviated ATM. This is on your equation sheet, but you'll need to use it on the test. So just make sure that you're aware that it's there. This is the SI unit. You can never go wrong converting to SI units. But sometimes, often in fact, I'll ask for the value in atmospheres, because that's sort of the more common unit that we use. What this means is 1 times 10 to the 5th newtons per square meter is that as we walk around at a pressure of 1 atmosphere, which is what we're at right now, at a pressure of 1 atmosphere, is that we have 100,000 newtons per square meter of pressure pushing down on us from the atmosphere. We'll talk about this in a bit, but it's as if you're walking around with this big column on top of your head. And that column is a column of gas that goes from here all the way out to the edge of the atmosphere. And you walk around with this weighing down on you all the time. And that's why the pressure, 100,000 newtons per square meter. Remember, a person is about 1,000 newtons. So it's like 100 people sitting on top of your head as you walk around with the atmosphere. The atmosphere all the way up to space, sitting on top of your head. Do you feel the weight of the atmosphere pushing on you? No. It's because, well, one, our body is almost completely water, right? And so it maintains its shape. But also because we have those pressures pushing at us from all sides, and so they cancel out the pressure of the atmosphere. Well, let me show you a video of this little experiment that this middle schooler does, where he demonstrates the atmospheric pressure. I think his name is Joey, I'm pretty sure. And it has cool music. And his mom, I think that his mom played an integral role in creating this video. That's not good. But anyway, it's a good video, so let's watch. So Jason, he lays down this newspaper. And by the way, if you want to do this, it's kind of tricky. So before you show your friends, you should really try it out a few times. And the ruler works a lot better than the pencil, because the pencil's kind of, it's not necessarily pointy. I don't use a sharpened pencil, but even a non-sharpened pencil is still a little pointy. The pencil will sort of break through the paper, so the ruler is better. Anyway, it's tricky because you have to get the paper sort of laid out flat. And you need a big sheet of paper. Think the Advocate, not the old nickel for it. Like you want a big sheet of paper. So he lays it out, and a sheet of newspaper is almost a square meter. So you have all this pressure that's pushing down onto the paper. 100,000 newtons, right, of net force pushing on this square meter of paper. And that's why the paper doesn't fly off, because you have the weight of the entire atmosphere pushing down onto that sheet of paper. Try. Right. Isn't that wild and wacky? So try it out at home with your friends. It's kind of cool, actually. Okay, so let me just put that in words. With a square meter of paper, the net force due to the atmosphere is 100,000 newtons. And so we've already said this, but let's put it in words and write it down. If the atmospheric pressure at sea level is 100,000 pascals, like it is right here and right now, the force on your body, well, the net force on your body, if you imagine that you're sitting here, you got a force that's pushing down in that direction, but you also have the same force pushing from up, because the atmosphere is pushing up on our chin as well. We have it here and here, but the net result of this, that the net force is equal to 0 on your body. And then also, your body is mostly fluid, or mostly liquid. I don't know, what's the percentage of water in your body? 90%? Is that true? I don't know. You're a biologist. So your body is mostly water. And it just doesn't, it doesn't bend to that. It's incompressible. Water is incompressible. We'll talk about that in a bit. Okay? Well, let's go and talk about the straw, because this is kind of interesting too. You ever use straws at lunchtime? Or at dinner or whatever? Draw a straw. This is a cup. It has a liquid in it, or cherry juice or whatever, and you put a straw in it. Now, what is the mechanism that causes you, when you come up to this straw, what is the mechanism that causes the liquid to go up the straw and then further go up into your mouth? Let's draw a little person here. There we go. It's a very large drink. And he's trying to drink out of this straw. So next time that you're using a straw, think about this. What is it that causes the fluid to go up into the straw and into your mouth? Now you're going to think that, well, it's because I'm applying a pressure inside my mouth. And that's sort of true, but it's also not really true. That really what's happening is you're creating a vacuum in your mouth, or at least a near vacuum, a lower pressure. You create a low pressure here. And then you have the atmospheric pressure that's pushing down with a much larger pressure than you can ever create inside your mouth, 1 times 10 to the 5th pascals, and it pushes this fluid up into the straw and then into your mouth. So whenever you're using a straw, it's not because of really what you're doing in your mouth. I mean, that sort of is true, but really the driving factor is the atmospheric pressure. I have another video I want to show you. This is from Veritasium. It's a little bit long, so I'm going to stop it about halfway. It's about the world's longest straw. There is a limit to how long a straw can be. We'll talk about it later when we get to manometers. But the limit of the straw, the longest straw that you could have is about 10 meters, about 30 feet. And this is where they talk about that, and they try to make a straw that's long. Let's watch this ad.